But I like the keypad on the side.
Nice having a cool keyboard.
There is just, I think it's just different name there. Like these are the ones that I have. MCOW is fine.
And I'm going to kill my video feed. I'm muted now, right? Why not? I click this. Am I muted now?
Try the other side.
Turn the camera off so that I can get full screen, because otherwise your screen is diminished. You can still hear me? So muting it doesn't make a difference. Am I muted now?
Test 1, 2. Test.
Yep, sounds nice.
Welcome in those of you that have joined us so far. We're working out a technical issue and waiting for a few more to join us. So give us just a few more minutes and then we will get started. All right, well, welcome in, everybody. This is Trig Minnick with MRG Labs. We are here for Grease Thief Thursday number 10, I believe. Today, we're going to discuss RDE, evaluating wear, contamination, and additive concentration. So today, we brought in a technical solutions specialist from Amatec Spectro Scientific, Lisa Williams. Lisa was also with MRG for 11 years prior to this in a variety of roles, including as lab and operations manager. She has a BS in chemistry from York College of Pennsylvania. She's been active in ICML. She holds a level 2 LLA and a CLS. So she's quite knowledgeable, and she'll be joined by Rich Wurzbach, our very own Rich Wurzbach, president of MRG today. For those of you that don't know Rich, he's involved in a lot of different things, part of helping out with new ASTM standards, especially the 7918, 7718, and also has been active with the ICML as a secretary of the executive board of directors, research consultant with EPRI, and way back when, he was a predictive maintenance engineer with Exelon Nuclear before he started MRG Labs, about 16 years ago. So you have those two excellent experts to guide you through RDE today. So I'm going to turn it over to them, and we'll go ahead and get started. Take it away, Rich.
Thank you very much, Trig. So, start off today, why do we run RDE on greases? So, RDE gives us the ability to compare an in-service sample to a reference baseline grease. And we're getting the value out of this in understanding our wear levels, contamination levels, and the ability to also identify grease mixing if there's is happening with that piece of equipment. In most assets, being able to isolate wear metallurgy can reduce the effort when trying to find the source of wear particle generation. So if you, as a laboratory, can identify that there is a large ingression of copper coming, they can go and they're going to know with the engineering department what components are going to have copper, and then they can go and check specifically for wear on those components. It can also help identify environmental or process contamination, and efforts can be made to reduce or mitigate that ingression. And we have some examples at the end, and we'll be able to show you how high wear or a environmental or process contamination is identified in our results. Some of the advantages of RDE is that RDE is effective for particles that are from dissolved state up to 10 microns. So one of the advantages there is the ICP is limited to about 4 to 6 microns. So it does allow us to see a few more particles. The RDE is user-friendly. There's a quick and easy sample preparation method. And a short time after you start that prep, you can take samples, run them, and get instantaneous results after your run. And that run time, as mentioned, is also very quick. It's about 30 seconds from the start of the test, and you have your results in hand and ready to review. So anybody that doesn't know, we'll just quickly go over how an RDE works. So at the top left there, you can see we have a sample cup. We have the carbon disc sitting in the sample cup and touching the sample that's inside the cup. And then above that is the graphite rod. The sample gets a excited electrical arc between the rod and the disc. This causes the sample to emit light. That light, you can see there's read by the fiber optical cable, and then it's brought into a diffraction gradient, and that breaks apart the light or separates it into different wavelengths. And then the different wavelengths of light are used to characterize the element that is emitting that light. And based off the quantification of that, you get the quantification of the element in that run. Sources of abnormal elemental concentrations. So as you're reviewing your grease report, understanding where some of these abnormal levels could come from. Spectroscopy methods test elemental concentrations of several metals simultaneously, but many elements can have multiple sources, and the analysis should be part of a holistic analysis. It's important to have baseline concentrations to help differentiate elements found in the additive chemistry and potential contamination. And that's a very important thing we can note on as a lab, that having that baseline sample adds a lot of value for the customer of not only identifying something like wear, but then also being able to understand how other additive concentrations have changed while the grease was in service. Some of those, just reviewing, zinc and phosphorus are common anti-wear additives. For example, that would be ZDDP. Sulfur, phosphorus, and molybdenum are commonly found as extreme pressure additives. Calcium and magnesium can be an indication of hard water contamination, but they are also used in engine oil detergent additives. So it is important when we see a certain element to understand the use of that equipment and what is expected as normal and then what would be abnormal. Sometimes for certain oils or greases, one response may be normal while another is abnormal, and that will change between each product uniquely. We also have silicon, sodium, boron, calcium, and magnesium, and those can be indicative of environmental contaminations. But we also do see silicon used as an anti-foaming additive. So that's where the baseline becomes valuable, and having that reference sample If it's in the reference sample and it's in similar levels in the in-service sample, we know that that's expected.
Hey, Richard, this is Rich Wurzbach. I'll make a comment on that. So foaming additives, anti-foaming additives, we don't expect to see that in greases, right? But another thing to think about is that there are some clay or bentonite thickened greases, and they will have silicon in there as an element. So when you talked about baselining, it's going to be more about understanding, is this a grease that in its initial formulation maybe has some silicon in it? And if so, we want to account for that and maybe look at a differential between that starting level, like we've seen in some of the bentonite thickened greases, and what we see from a used sample.
Thank you very much for that comment. And then obviously when we see common wear metals such as iron, copper, chromium, tin, aluminum, and lead, it's going to suggest our wear conditions, and if we would see those increase sharply between sampling periods, we know that there would be a change in our wear generation weight, and we need to, at this point, possibly suggest, maybe advanced analysis, including something like analocalphorography, to look at the increased elementals that we're seeing that wear and identify, are these abnormal wear conditions that are causing the generation or normal, so that way customer can make the correct decision. So here are the elements, just to make it a little bit easier in a chart form. So there you see at the top most of our wear metals, but as noted, some of those can be used as an additive or contamination. Another one I'm thinking on this is you will have one of our examples is with an aluminum complex grease. So you can see them. So that's, like Rich pointed out, having that baseline is extremely valuable in understanding where you started and how your in-service sample has changed. In the middle of the chart there, we're getting into the contamination or additives, and that kind of continues that trend down on our chart. So next we'll talk about the RDE calibration. So the calibration on the RDE is performed using a 0 ppm, a 100 ppm, and a 900 ppm dissolved oil standards. And that is performed, that's routinely when the unit needs standardized. Each day you have a daily check where you're running the standards, making sure that it gets the correct reading, and you're ready to go. Note we have there is that there are some users that may want to calibrate above the standard calibration range that we have listed there of 0, 100, and 900. And if a customer would choose to do so, that is something that Spectro can assist with in that process to set you up with that.
Yeah, Richard, this is Rich Wurzbach again, and that's really something to consider, because if you think about the 0, 100, and 900, the 0 and 100 run the whole spectrum of metals that you might look at. The 900 is really limited to a subset of elements that generally correspond to detergent levels that might be much, much higher in oils, certain detergent fortified oils. So it makes sense to calibrate at those different levels. When we think about greases, there's not really that kind of detergent chemistry showing up in most greases, but we do get much, much higher wear levels from an accumulation perspective in grease, because grease is cumulative. Unlike oil, where we've got filters and particles can settle and so forth, it tends to limit the accumulation. Grease will accumulate these wear particles over time. So it's quite common that we get samples with thousands or even tens of thousands or even hundreds of thousands of ppm. And so in that kind of situation, it's worth considering, should we create a different kind of calibration span here that helps us better report these higher values?
So I think that's really where Spectra was coming from when we decided we needed to go ahead and offer that extended range from expanding on from 900 parts per million, just because all of those ranges tend to be above that 900, and really capping out at 900 does not fit into some quality programs. So as a result of just speaking to some customers, that was some feedback that we got to be able to extend that calibration range would be really helpful.
Thank you very much, Lisa and Rich. So then on to our sample prep. This will be a paper that Lisa actually wrote, and I will post in the comments during Lisa's demonstration. But the sample prep from Spectro, you want to use a 1/2 gram of grease, and that's going to be dissolved in 10 milliliters of a heptane toluene solution that is in a 50-50 mix. That sample is then shaken or agitated, and then when the sample is completely dissolved, it is ready to run. And there you see on the bottom, you have a 1/2 gram of grease in the vial, 10 milliliters of solvent has been added, and then after a short period of time, the grease is completely dissolved. And something that we note on there, sometimes we have some customers that do struggle to send us a full sample size. So at our lab, we have had to use smaller sizes, and we do a ratio where same thing where you're going to that full, where it's 0.05 grams to 1 milliliter of solution if you do not have the full 1/2 grams to meet the requested amount from Spectro. And we can see Rich was holding up a sample vial and the substrate that it would come off of, and then the dissolved grease that's sitting in the vial ready to go.
Yeah, Richard. So this is you can see kind of a darker color here, and we're starting with a darker grease. And this substrate, we've already removed a couple of these sections. You can see the remaining grease from that sample, but we dropped 2 of these in here. It might be tough to see, but if I turn it on edge there, I think you can see 2 of those substrates dropped in. Each of these substrate sections holds about 1/4 gram of grease, so it gets you to about a 1/2 gram for the purposes of this measurement. But you won't always see the sample looking like this. This is one of the ones we set up for Lisa to test here in a few minutes, but here's another sample. And you might think this is from a new sample, but it's not. But it does have a lot of that original color of that grease still present in this diluted state, but there is quite a bit of metallic content nonetheless.
Thank you for that, Rich.
So another way that you may do this is if you don't see it on a substrate, you may also see it in a grease boat from if you're using an instrument like the FerroCheck, or if you have taken a sample and it's not on a substrate, you need to make sure that you're measuring out 0.5 grams. So that 0.5 grams is going to be critical. And if you're not aware of what that weight is, make sure you get that weight. So like Richard said, you'll have to account for that weight difference and possibly apply a dilution ratio, if not, to make sure we can get it up to that 0.5 grams.
Thank you very much, Lisa. So next, on to interpreting our results after we prepared our sample. So the significance, we get the elemental concentrations to track multiple risk factors in our lubricants. As we mentioned, we'll be able to track our wear accumulation. We can look at environmental contamination from outside of our machine or part of the process. It could be additive composition, and then helping us identify grease mixing. On here too, you see we have that a dilution factor can be used, but does not need to be. The most important thing on here is when you determine this with Spectro is the consistency in which you report. If you start with a dilution factor and you report out those numbers, it's important that then you always report with the same dilution factor. If you start and you do not report a dilution factor, it's important then that you would keep that trend and report the results as is and without a dilution factor. You have something to say, Lisa?
So Richard, if I could
Yes.
just add a couple comments about the dilution factor. So I think one important thing we all need to understand and realize here is there is no standard method out here for how to run a grease through a spectrometer. And that's one thing that we're working pretty diligently at ASTM, is to really standardize how to prep a grease and enter a grease into the spectrometer. And that dilution factor can be a debatable issue. And like you said, it's going to be really important to keep it consistent, how you're trending those results. So I get a lot of questions about how to set alarms and what's normal, what's not normal. Well, if we're not being consistent in how we're trending the results, there's no way that we're going to be able to set those statistics. So it's going to be very critical to understand whether or not you've applied a dilution factor or not, and be consistent in how we're applying that.
Yeah, Lisa, this is Rich. So, we had a little discussion earlier about, some people use RDE, some use other methodologies. They may be using ICP, maybe even XRF. And it really comes down to the consistency of method, consistency of dilution, preparation, because once you change these variables, you're really out of the realm of being able to apply some kind of standard criteria or something to say, here's an action level, right?
Thank you guys very much for that important points on interpreting our results. So here we have a couple examples to show from our examples. So on top, the first example we have circled in red is a customer that had a grease that had severely elevated iron levels. And we can see that they are up at almost 16,000 parts per million. So it's quite high, and that this was a big change from their normal. Their normal levels was between about 75 and 110. So seeing that large jump up, they knew they had an issue and initiated further advanced testing to find the culprit or the generation of that increased iron wear. The second example we have here this is from a main bearing of a wind turbine. So here we see a very highly elevated levels of copper. And upon completion of analytical ferrography, we were able to determine that there was a lot of laminar wear, copper alloy particles on the slide, and gave that feedback to the customer, and they went back up tower, and this was relating to a cage issue on their main bearing. So just wanted to leave.
Yeah, Richard, and while you have this up, this is a good time to talk a little bit about how you interpret these numbers and how they might vary depending on the circumstances. And you started by telling us that the RDE is measuring up to about 10 microns in particle size. And if we remember back to some fundamentals training on large wear, abnormal wear, normal rubbing wear, that line is right around 15 microns for a lot of these wear modes, such that small normal wear is less than that. Large, abnormal, severe wear is greater than 15 microns in many cases. So we had to actually migrate out of the sweet spot of this technology, and really most of the used technologies for that. So it can be very good to complement this technology with a ferrous density type measurement. And of course, in our we've talked about this in some of our earlier presentations. There's a number of products out there that allow you to do this, but in doing so, if you have information both about ferrous density and this elemental iron, it looks at different aspects of what's going on. For example, we could have a wear mode that is primarily rubbing in nature. It might be adhesive wear or abrasive wear, and it produces large unoxidized particles. You're not going to get a very strong response in your RDE spectroscopy for iron in that case. On the other hand, you have some kind of corrosive process, some wear process that's oxidizing in nature, such as fretting wear. That's going to create an oxide, and the oxide is going to show up very well in this technique because it tends to make very small particles, but not so much in those ferrous density type measurements that would rely on the ferromagnetic character of the individual particles, and they might respond a little less there. So these two approaches are very complementary, but we We don't want to look at this in a vacuum. When we see data like this, we want to be thinking about what kind of wear mode could this be? What size particles am I dealing with? And does this tell me the whole story about wear particles that are being generated?
Thank you for that.
Completely agree with that. One of the things I absolutely love about elemental spectroscopy is that it's kind of like a landing ground to shoot you in different directions of where is the data taking us. And if I could just add to that, complementary between the ferrous density and elemental is when I do analytical ferrography, I love to have this data sitting right beside me. It kind of serves as a self-check for me of like, what I'm seeing? Am I seeing what I'm supposed to be seeing? Of course, we can see a little bit larger particles in ferrography as well, but having all of these three technologies paired together is such a valuable tool, and learning how these technologies work together as a puzzle is just a really valuable problem-solving tool.
Thank you very much for that. So on to another example we have. This one was from a customer that's in the pulp and paper industry. Specifically, this is from a pump, and it was contaminated by the process. When we originally saw the levels in our analysis, we reached out to the customer. We're asking them about different greases they had. If you see the calcium, it went from very low at 1.7 ppm to jumped up to almost 300 parts per million. So we started talking to the customer. We had first thought this might be due to grease mixing, and then we found out some more information about the area that this piece of equipment was doing work in. And we actually got the feedback that the elements that we were seeing increasing were present in the room, and that they were then ingressing into this into the bearing, and then it caused the issues that the bearing went and eventually caused the failure of it.
Yeah, Richard, it's a great case. In the pulping industry, you have process fluids called liquor, black liquor, white liquor, and so forth. And I think this really goes to, again, not trying to do lubricant analysis in a vacuum. Understand as much as you can about the application and the environment that the equipment is sitting in. And I say sometimes it's a good idea, to tell somebody, when you go to take the sample for me, sweep a little dust up off of the floor, put that in a bottle, and let me look at that as well, because it might give me some indications of what types of elements are there and in what ratios. Dave Turner was talking about ratios in the sidebar conversation earlier with respect to what's in some clay thickened greases. But if we know what's in the environment surrounding the equipment, what kind of elements are present, what ratios are they there in, it becomes a kind of a trigger point for us to say, this is a contamination issue. We know where it's coming from, and it corresponds to the environment that this is working in.
On the next slide, we have some examples of actual grease mixing that happened with different customers. So here on the top one, we can see that we have a change in our silicon and boron additive levels. There was an extreme drop in calcium. So we're using some kind of calcium sulfonate or calcium complex grease as our baseline. And it is now not there, and that was going to, that's going to draw a big indication in the lab if that calcium level depletes like that, that somebody has replenished this bearing with the incorrect grease. And then that's also further confirmed where we see a change in our phosphorus to zinc ratio. So we see our complete loss of phosphorus and a severe depletion or decrease in our zinc level compared to that reference baseline. And then at the very end, we'll see the FTIR confirmation. That also kind of what we've been mentioning about kind of tells the whole story, putting all this data together, that the sample is clearly not like the reference baseline, and it has changed while it's been in service, or it's been changed while it's in service due to the adding of the incorrect grease. And then down below, we see the similar thing happening with the second example.
that FTIR conformation number, I actually love this concept in oil analysis and lubricant analysis of taking and trending numbers and coming up with a value, an algorithm, if you will, that helps us quickly understand whether or not we need to take action. I just feel like that is such a key concept for us who don't have a lot of time, need to see something quick and understand whether or not we need to move forward. We at Spectro have a concept like that as well, where we do it's more of like an identify fluid kind of thing where we have a number. But I love this concept just because it's a quick, easy way for us to know whether or not we need to move forward with a more robust analysis. And I think that really is a key thing in the lubricant analysis industry as we move forward.
The lower sample here, we can see that the baseline had an even higher amount of calcium as an additive starting out with. And we saw the same idea where our additives have been depleted or changed with the addition of the incorrect grease. We lost that calcium, so we're mixing our thickeners. We've lost our phosphorus and zinc in there as additives. And then here we see an even more extreme change in the FTIR conformation. So it's even lower than the previous example. So these are greases that are extremely different.
Yeah, Richard, I'm gonna modify your phrase there from "we've lost calcium" to "it probably was never there." When you see this big of a difference between a very, very high calcium level, which almost certainly tells us this is a calcium thickened grease or a combination of calcium and something else in the thickener chemistry. When you've been able to knock it down that far, that tells me calcium never got even into that machine. And this might be a customer that believes they are lubricating with a calcium grease, but what's really going on in the plant is some completely different grease is present. And that can be very eye-opening. Yes, it can set you up for mixing problems, but that facility may not even be using the grease that someone has specified for that machine. It may be a grease that's inappropriate altogether.
That 23,000 ppm, excuse me, for calcium just kind of reiterates our need for possibly expanding that calibration curve on the RDE. We see these really, really large values. So from a quality standpoint, it is wise to extend out that calibration, especially if we're using these really high ppm thickened greases.
Yes, thank you very much. All right, so now do we have any questions in our chat? I know that I saw a good one. I'll read it off, Lisa, and then if you'd like to have a comment on that, you may. And then if you don't, I can also comment in our laboratory how we've dealt with this issue. But the question is from Bobby, some greases do not dissolve. What do you use? So he's asking specifically about a PTFE grease, and it's not going to dissolve in our typical heptane toluene solution.
Unfortunately, PTFE greases are one of the more challenging greases we have to deal with, and there's a number of reasons why. I'll come on to camera here. There's a number of reasons why. So the PTFE is a fluorinated grease. So without getting too heavy into the chemistry, fluorinated greases are very difficult to excite in the RDE. So you're not going to get full excitation of that grease in the RDE. You will be able to dissolve some of it, and you will be able to run it in the RDE, and you will get a number. It just won't be as precise as it could be. So you can certainly run it and get a number, but whenever I run it, I always preface with that little blurb of this is a number. We're simply trending it. This is not an exact number, but there is some value when you can at least trend it. And as long as you're measuring out that 0.5 grams and getting some kind of dissolve, I think maybe, I'm just kind of thinking out loud here, dissolving it and using the same dissolve time may be a way to keep some precision. But PTFE greases are one of the more common or one of the more difficult greases to run in the RDE. I wish there was a recipe book.
Right. So I'll add to that and say that the Teflon can be there as a thickener, can be an additive. How's that?
Very good.
Okay, super. So yes, when we talk about Teflon, we first have to find out if we're talking about a formulation that has had Teflon added as an additive, or are we talking about a Teflon thickened grease? If it is a Teflon thickened grease, there's a lot of possibilities for what has been thickened. For example, a polyfluoropolyether can be a base oil can be thickened with Teflon. And then you've got two concerns about how do I choose a solvent for this system, the grease system. And you could have some Teflon greases that react very well to one particular solvent choice or solvent system choice, and then a different Teflon grease that performs quite poorly. So it's almost on a chemistry specific basis that we need to experiment a little bit and find these things. But one time we had a project, we were working with a particular Teflon thickened polyfluoropolyether grease. We worked with the supplier of that product who had worked out a chemistry of a solvent that worked quite nicely with it, and we had to go in that direction. What becomes tricky is when you deviate too much from the kind of the traditional hydrocarbon solvents that we're using for most greases, and then you want to go on and do something like analytical ferrography. Keep in mind that the principle of analytical ferrography is this solvent that you're choosing works with the film that's on that glass substrate. And if you choose a different chemistry to dissolve the grease, it may not optimally work with the substrate for ferrography. So there's some kind of secondary impacts down the line as you use these solvent systems. So I think that there's here we use a combination of solvents, and we share that with some folks that are using our equipment and things like that. You're right, Bobby. It won't work for every grease that's out there, but it's good to recognize when it doesn't, and then take those efforts to find a system that does work. Before I kind of turn this over to Lisa to show us, her company's equipment here, the Spectro RDE, I want to talk a little bit about how we get to that point from the grease itself. And if you're just starting with a glob of grease, it can be tricky, especially the solvent selection process and how effective it is. And so what I'm showing here is, what I had up a moment ago, which is our substrate. And the substrate is coming from the grease thief analyzer. And those of you who were in our sessions a couple of weeks ago saw us using the grease thief analyzer, saw us doing particle counting with the grease that would set down on the substrate. But once we have this substrate, what's nice is we have a thin film of grease. And it really makes a big difference when you go to dissolve this grease if you're starting with a glob or you're starting with this extruded thin film. When you have the extruded thin film and then it ends up inside this, your kind of container that you want to add your solvent with, you have this large surface area and the ability to agitate that very effectively. And as you can see, we end up with a clean substrate when we're done, which tells us that we've done a nice job at dissolving that and getting the particles suspended and getting the grease dispersed. And so it's from this starting point that we're now going to pivot to Spectro's equipment here and show how you're going to run this kind of sample. This is different than an oil sample in that an oil is going to have a different flammability impact than this preparation because of these lower fraction solvents. And you're going to see some differences in how you might do oil. But I'm going to ask Lisa to show us on the Spectro RDE machine.
Okay, so I'm going to talk about the procedure for how to do this. And one of the things I love about this capability is the fact that if you're already doing oil analysis, it's just a quick shift over, and you can add grease analysis into your program as well. So there's a procedure that Richard is going to share at the end of this. As I have this all typed up, I'm just going to go through this procedure, and I'm going to give you some little tips and tricks. I get a lot of questions about how to do this, how to add this capability to your oil analysis program. I'm demoing today on a Spectro M unit, but Some of you may have a Spectral 120. It also works on the Spectral 120 too, that tower. So we can use the same methodology there. So the key here is going to be, sample prep and making sure that we have a good volume of sample. Whether or not we need to decide whether or not we're applying that dilution factor. So we need to understand that. And then it's a matter of making sure that we have standardized our equipment and checked our calibration and then gone through that PM process to make sure that everything's gapped and working correctly. So I'm going to assume that we've done that already, because we have in this case, but assuming we've gone through that whole process of making sure that our instrument is calibrated and standardized, and then we're ready to go. So like Richard mentioned in the presentation, MRG has their standards laid out here. So they have 0, 100, and actually I'm mixing them going backwards here. So 0, 100, 900 parts per million. So like we've said a couple times here though, a lot of our greases, especially just in the grease realm, in the oil realm, this isn't an issue. 900 ppm is usually plenty. But in the grease realm, we're usually seeing those values that are well above 900 parts per million. So to be able to extend that calibration range is going to be helpful in some cases. Some people may have a quality program that says you must do this and has those checks. So being able to extend out that range is going to be critical. Just contact, well, you have my information, but just contact Spectre Scientific Support Team. They'll be able to set you up with that extended calibration and show you what products you need to buy to do that. So I have a couple samples here. So we'll run the one that's darker, that's probably a little bit more exciting. So we have a sample here, and these vials are just, they're just a few milliliters, and you're going to take your 0.5 grams of sample. So it's important to understand what that weight is. If it's like give or take 0.5, that's not a huge deal. If it's like half of 0.5, then we definitely want to be accounting for that in our dilution. So this is a heptane toluene solution, okay? So this is going to be your standard. That's what you're going to try to do each time. Use that heptane toluene solution. And like I told Rich a couple minutes ago, I wish there was a recipe book. It would be great if we had a recipe book of solvents that work for specific greases. There isn't anything out there that exists. So we start out with try heptane toluene, and that is what we're going to use. So we have a stand that the sample goes into. And then we also do have the cups. Oops, that's not the cups. There they are. So the RDE sample cup. So this is just a black cup. Spectre Scientific sells these. It's a consumable for the instrument. So this black cup is what you're going to use. You use it for your oil samples. You're going to use it for your grease samples too. If you're worried about the black cap burning up, don't worry. It will melt a little bit, but it will not burn up, okay? It's nice because it's just a disposable thing and you can just throw it away. So once your grease sample is dissolved, obviously this is going to be a little bit more volatile than your oil sample, unless your oil sample is really contaminated with something. This is going to be more volatile. So what we're going to do is we're going to use the shield, and it's called a fuel shield. This will be on the instructions that I provided that you can get at the end of this. But this is a fuel shield. Spectre Scientific sells this. These are reusable. They're made out of aluminum. And you can simply just wipe these off with alcohol wipes. You can wipe these off with any kind of mineral spirit is fine. So they're reusable. And everything else is going to be a consumable. You have your rod. Just like with oil analysis, you got to make sure that that's sharpened. You got to make sure that that's clean. You got a nice tip on the end of it because you're going to create that spark. So I'm going to go ahead and I'm going to prep the sample. It's exactly as you would do to run oil analysis. You have your sharpener. I'm going to go ahead and sharpen my rod and put that in. And then you have your carbon disc. Again, exactly the same as with an oil sample. I grab a Kim wipe here. You always want to make sure you're not touching the carbon disc with your hand. You want to make sure you're not contaminating that. They're porous for a reason. We don't want any contaminants in there possibly introduced into the sample. And we're going to shake up our sample real well. Okay, make sure it's dissolved as best as it can be. And suspended as best as it can be. And then you're going to fill your cap up. You're going to smell that heptane toluene. Don't be alarmed. And we're going to stick this into the spectrometer. Now, normally, we'd be good to go with an oil, but for the grease, we're going to cover this with our fuel shield. We want to minimize those flames, and then the cup is just going to come right in and fit in to the spectrometer. Then we're going to gap our rod accordingly, make sure everything's gapped properly, and then we're going to go ahead and hit start. So like I said earlier, one of the things I just love about the spectrometer is we're going to get a wealth of information from wear to contaminants to additives, and we're going to know, once we see what we get here, we're going to know which direction we want to go. Which instruments do we need more information on? Maybe we need to take an FTIR and understand what's going on there. Is there grease mixing going on? Maybe we need to run analytical ferrography. Maybe we need to get some more information from a grease mixing standpoint, those sorts of things. All right, so my results, I have some lead, I have some iron, quite a bit of sodium, assuming that's probably dirt. And then I got some zinc, little bit of zinc, very little, and some phosphorus. So depending on the darkness, since that grease was dark, I'm wondering what else might be in this sample. So I don't have a whole lot of background about this sample, so I'm simply speculating at this point. But we're in good shape here. So as far as next steps, I'm going to go over cleaning now. So one of the very important things with running your grease sample through and running a more volatile material through the spectrometer, you're going to create more of a flame. So flames create soot. So we want to be very careful that each time we run this sample, run a grease sample through, and we're creating that flame, that one, we don't touch the parts right away because they are going to be hot. Two, we want to make sure we dispose of our mineral spirits properly. We don't just want to pitch them in the trash, just like with oil. And three, we want to make sure we wipe down our chamber really, really well because we created more soot than we normally do. So I'm going to show you how to do that now, and then we'll be ready to go and all done. All right, so typically what you can use here, I'm just going to throw this in the garbage. Typically what you can use here is just a Kim wipe. Should be able to wipe everything down pretty well. Now, if you have an extra amount of soot, which I don't really see in here right now, this is actually a pretty good sample. Simple green works really well inside the chamber to get rid of any soot. And then Windex works as well. So like start with simple green and then get all that wiped out real well, and then finish with Windex, which I believe Spectra Scientific does offer little bottles of Windex that you can purchase as well. So this actually looks really good. You guys cleaned this out really well. I could tell. All right, so that is how to run a grease sample. And like I said, now we are ready to run the rest of our tests around the lab and get some good results to help put those puzzle pieces together. And thanks for your time and letting me show you how to do this.
Yeah, can you hear me now? Great. Well, Lisa, thank you. I thought it was interesting that you selected the darker grease of the two, yet you didn't get much of a response on Spectro in terms of like high elemental values. And it really underscores the importance of creating a broad test slate that looks at a lot of different parameters. Sometimes greases start very dark, or this could be strictly an organic degradation process. So We do learn a tremendous amount by looking at the values that we get out of RDE spectroscopy, but it's one set of data that we really want to be complementary to other things that we're discovering with our full test slate of grease analysis. So, Richard, did we see any other questions come in? I did try to answer some things that I saw there while Lisa was talking. We can open it now for any other questions or discussion. And I can't hear you yet.
I had Bobby's question, and Lisa did put a very nice written response in the chat about the PTFE greases, and she was they both were talking about Krytox, and she said that Lisa said that they were able to get the solvent from the from Chemours, and they worked on that. However, that mixture wouldn't work with ferrography slides. So it's like, kind of like what we talked about during the presentation, that it may work and dissolve for RDE, but then we might run into an issue with a different test.
Yeah, and I don't want to force Lisa to say anything, but that was me sitting at her computer a moment and typing a few things in. But
sorry,
she was nodding along, and she's aware of that as well. And I think she would have backed that up. I didn't realize I was typing on her behalf there. But no, it's a good question. And we have to think through the implications of it, which is, now that we have that solvent, what do we need to do? Maybe we need to filter the particles out so we get away from that solvent, because it can have a lot of implications for other tests down the line.
I feel like I looked at one of those.
You seem to be muted, Lisa.
There we go. I feel like I looked at one of those greases before, and on ferrography, and I can't remember. Did I see white particles? Is that common with PTFE? Like you could see like white, like Teflon-y type. I remember it forming like a pasty kind of. And you didn't hit it. You don't have it right if you're seeing that. So.
Mm-hmm. Yeah, you mean in analytical ferrography, right? Like and this is, to be honest, analytical ferrography is where you find out, did I do a good job with my solvents or didn't I? And it can be a moving target as well, because remember, we're not testing the pretty new grease. This is stuff that's been beaten up, and so sometimes there's been some chemical changes that have already happened. Maybe there's been a little bit of mixing. Maybe there's been high temperatures. Maybe we even have what we might consider varnishing in oil happening in this grease. And when you do that, it might change and diminish the solubility of the things that are in that grease relative to what it was when it was new. So I'm just saying, be prepared to be in an imperfect world when we're relying on the selection of some solvents to help us prepare. It's almost like sometimes with ferrography, we have to peer around certain things that we didn't get fully dissolved and figure out what's the real stuff of interest, what are the real wear particles that we want to identify, evaluate, and so on. I'd like to thank Lisa Williams, that asked her to come back up here again and take some credit here today for coming back to our laboratory. Thanks, Lisa. And as you've been going out in the world, you've obviously learned a lot more, which is fantastic, and it's great to get back together with you and share the time here to go through these topics. And I hope we can do it again. All right. Hey, Trey, can you talk about what we got coming up next time? By the way, thank you to Richard Janoski as well for kind of leading us through as we're standing out here in the lab and keeping us following through the process. Thank you, Richard.
Yes, thank you, Richard, for the presentation part at the beginning. Yes, next week we are going to go into grease compatibility. You may have noticed that there's a slight change of schedule. We are going to cover grease compatibility, analytical ferrography, and wind industry, I believe, are our next 3 in a row. So we're going to move grease compatibility to next week and talk about how we do the studies for that and help you avoid common issues that we see when changing greases.
Great. Thanks, Trig. We'll be back in the lab for that, standing at our test stand where we simulate those conditions, and look forward to being a part of that.
All right. Great, everyone. We'll look forward to seeing you next week. Thanks.
What we do.